Imagine you are cruising down the interstate at 60 miles per hour. Suddenly, you hit a single, deep pothole. One sharp jolt and boom, your tire shreds, your rim is mangled, and you are left stranded on the shoulder of the highway. It is a violent, sudden reminder of how fragile our everyday technology can be. Now let's change the scale. Imagine a massive commercial airliner, a 200-ton beast of aluminum and steel, screaming toward the ground at over 160 miles per hour. This is the critical moment of touchdown. At these speeds, the friction between the tire and the concrete is so extreme, it can reach temperatures high enough to melt lead. The runway effectively becomes a racetrack of fire, a brutal arena of intense heat and kinetic energy. And yet, the only thing separating this half-million-pound machine from a catastrophic crash is a few circles of black rubber. On paper, it looks like a fatal design flaw. It feels like a total paradox. Why would elite aerospace engineers, the same people who build multi-billion-dollar stealth jets out of titanium and carbon fiber, trust something as seemingly simple as rubber to handle this kind of extreme punishment? Why doesn't the tire simply vaporize or explode into a million fragments the second it makes contact with the pavement? You might think a complex system of metal gears or heavy-duty hydraulics would be the logical choice for this underdog role, but the truth is actually much more impressive. The aircraft tire is not just a piece of rubber, it is one of the most sophisticated, over-engineered components in the entire history of aviation. To see why this humble material is capable of surviving the impossible, we first have to understand the sheer violence of the environment it lives in. Because once the smoke clears, you'll realize the real battle is just beginning. To see why this plane refuses to die, we first have to crack it open and understand how it actually works. But before we get to the internal gears and the heavy armor, we need to look at the exact millisecond of contact. When that landing gear drops and those wheels lock into place, they are essentially dead weight. They aren't spinning. They are hanging there, cold and static, in the thin, freezing air of 30,000 feet. But in an instant, everything changes. As the plane descends, the pilot isn't just aiming for a gentle landing. They are essentially initiating a high-speed collision with the Earth. When the rubber finally meets the concrete, it doesn't start rolling immediately. For a violent, split second, it skids. Think about that. Imagine taking a pencil eraser and dragging it across a desk at 250 miles per hour. That is the sheer brutality being inflicted on a tire that costs more than a luxury sedan. In less than half a second, roughly the time it takes for you to blink, that tire has to accelerate from 0 to over 2,000 revolutions per minute. It is a mechanical explosion of kinetic energy. This is why you see that iconic puff of white smoke during every touchdown. That isn't an engine backfire, and it's not a malfunction. That is the tire literally sacrificing a thin layer of its own body to the runway. It is sacrificial rubber, a high-stakes trade-off where the tire gives up a fraction of its mass to gain the traction needed to keep the aircraft from sliding off into the grass. But the speed is only half the story. The real horror for the rubber is the crushing weight. When the full mass of a Boeing 777 or a heavy-duty cargo lifter settles onto the landing gear, the tires undergo a transformation that looks like it defies the laws of physics. If you were to watch this happen in extreme slow motion, you wouldn't see a rigid, sturdy wheel. Instead, you would see the rubber compress and bulge outward like a piece of jelly being smashed by a massive sledgehammer. The sidewalls distort so violently that they look like they are about to buckle and snap under the pressure. Engineers call this deadly elasticity. It is a delicate, calculated deformation. If the tire were too stiff, it would shatter like glass upon impact. If it were too soft, it would simply roll off the rim and send the plane spinning out of control. It has to be the perfect middle ground, a material that can act like a liquid to absorb the initial shock of the landing, but recover its solid, circular shape in a heartbeat. Think of the tire as an Olympic weightlifter. Imagine a man trying to hold 500 pounds over his head while sprinting at a full-speed dash. His muscles aren't just holding the weight. They are vibrating, flexing, and absorbing the impact of every single stride. That is exactly what the rubber is doing. It's a high-performance athlete made of complex chemicals and high-tension cord. Every single landing is a maximum effort lift. The heat generated by this process is staggering. Within seconds, the internal temperature of the tire skyrockets to levels that would boil water. This isn't just warm to the touch. This is a thermal shock that would cause standard air to expand so rapidly it would blow the tire off the hub like a grenade. This is where the battle of friction truly intensifies. We are talking about friction levels that turn the contact patch, the small area of the tire actually touching the ground, into a microscopic furnace. The rubber is being pulled in two directions at once. The plane wants to go forward at 200 miles per hour, while the runway is forcing the tire to stay put. This tug-of-war is so intense that the rubber actually starts to liquefy at the very surface. It creates a microscopic layer of molten high-tech polymer that acts as both a lubricant and a brake at the exact same time. It's a chaotic, violent dance between the machine and the pavement. So, how does it survive? How does a material we usually associate with rubber bands and garden hoses stand up to this ruthless hunt by gravity and heat? How can it be an elite athlete and a shock absorber at the same time without failing? To understand that, we have to look past the black charred surface. We have to peel back the layers and see the hidden engineering that makes this rubber more like an armored fortress than a simple car part. Because the secret isn't just in the rubber itself, it's in what is hidden deep inside the casing, and the invisible gas that keeps the whole system from becoming a ticking time bomb. Let's start from the inside out and see how this mechanical underdog actually handles the pressure. To understand how this rubber underdog survives, we have to look past the charred surface and go straight to the heart of the wheel. Most people think a tire is just a bag of air, but in aviation, standard air is the enemy. Regular air contains moisture and oxygen, two elements that react violently when subjected to extreme heat. If you fill these tires with the same air you put in your car, the oxygen would actually ignite from the inside out during a heavy landing, causing an internal explosion. That is why engineers use pure nitrogen. It is dry, it is inert, and it does not support combustion. But it is the pressure that really shocks the system. Your car tire typically sits at about 32 psi. This tire, it is pumped up to over 200 psi. That is more than 6 times the pressure of a standard vehicle. To put that into perspective, imagine the entire weight of a 6-ton African elephant perfectly balanced on your thumb. That is the kind of concentrated, invisible force we are talking about. The pressure inside is so high that the tire isn't just a cushion. It is a high-pressure vessel, essentially a stable, non-exploding bomb designed to take the hit of a 200-ton aircraft without flinching. It is the rugged engineering behind this internal pressure that keeps the rubber from collapsing under the crushing weight of physics. Without this nitrogen-filled core, the tire would be nothing more than a limp piece of rubber, incapable of supporting even a fraction of the plane's mass. Now, step over here. We could slice this casing open like a piece of fruit. You would realize that calling this rubber is like calling a skyscraper a pile of rocks. Let's take a look at the cross-section. Beneath that outer skin is a complex, layered tactical network of materials. First, you have the beads. These are massive bundles of high-strength steel wires that lock the tire onto the rim, ensuring it never slips even under maximum torque. Moving deeper, you'll find the carcass plies. These aren't just thin fabrics. They are high-tensile steel cords and synthetic fibers like Kevlar and specialized nylon, all braided together for maximum structural integrity. To give you an idea of the scale, let's compare the strength of these fibers to a person. You can see just how tiny a single thread is, yet when woven together, they possess a tensile strength comparable to the massive cables used to hold up the Golden Gate Bridge. They are designed to be flexible enough to absorb the initial shock of a landing, but rigid enough to prevent the tire from ballooning out under that 200 psi of internal pressure. And notice something missing? There is no inner tube. These are tubeless tires. The rim and the tire create a perfect airtight seal. This design prevents the friction and internal heat buildup that an inner tube would cause, which would be a death sentence at 250 miles per hour. It is a literal armor-plated shell made of fabric and metal, encased in a high-tech polymer bathtub. But let's consider a worst-case scenario. Imagine a rejected takeoff or a landing where the pilot has to slam on the brakes at maximum capacity. The kinetic energy has to go somewhere, and it is converted entirely into heat. Within seconds, the brake discs start glowing a bright demonic orange, and the temperature transfers directly from the wheel hub into the tire. The internal temperature of the nitrogen gas begins to skyrocket, reaching over 200 degrees Celsius. In a normal tire, this would be the end. The pressure would spike to catastrophic levels, the rubber would fail, and the tire would explode like a fragment grenade, sending supersonic shards of metal and rubber through the wing and the fuel tanks. But engineers have built in a secret defense mechanism. If you look closely at the wheel hub, you will find several small threaded plugs. These are called thermal fuses. They are essentially the silent guardians of the aircraft. Inside each plug is a special metal alloy with a very precise melting point. When the heat reaches a dangerous threshold, the alloy melts away, opening a small vent. Instead of a violent explosion, the high-pressure nitrogen hisses out in a controlled, steady stream. It is like a safety valve for a steam engine. It deflates the tires safely before the pressure can reach the breaking point. This simple piece of melting metal is often the only thing preventing a multi-million-dollar disaster. It is the ultimate fail-safe, a quiet piece of genius that ensures that even when the physics of heat and speed are at their most aggressive, the plane stays on the ground and the mission ends safely. This C-fuse is the reason why, even after the most brutal landing, the aircraft remains a stable platform rather than a wreckage. So, the next time you look out that window and feel the slight jolt of the landing gear deploying, remember the violent battle about to take place beneath your feet. It's easy to get caught up in the roar of the massive jet engines or the elegant curve of the carbon fiber wings. But at the end of the day, your safety, and the safety of everyone on board, rests on a few circles of over-engineered rubber. It is a testament to human ingenuity that we can take something as ordinary as a tire and turn it into a high-pressure fortress capable of surviving the impossible. Behind every smooth touchdown is a legacy of hidden inventions, from nitrogen-filled cores to melting metal fuses, all working in a perfect, layered tactical network to keep you safe. If you found yourself holding your breath during that simulation, or if you simply feel a little bit more confident about your next flight, consider subscribing to the channel. We take pride in peeling back the layers of these technical wonders to show you how the world really works. Our team spends hundreds of hours researching, scripting, and handcrafting these animations to ensure every detail is accurate and visually clear. We make original videos from scratch, animated by humans for people who never stop being curious. The aircraft tire is a reminder that in the world of high-stakes engineering, there is no such thing as a boring part. Every bolt, every wire, and every thread has a story of survival. But it makes you wonder, what other ordinary object is hiding a secret of extreme physics? Let us know in the comments what we should crack open next. Thanks for watching, and we'll see you in the next one.